Thanks for the invitation to speak here today to WISS. Yes, and I'm going to talk about life on Mars. So I will talk a little bit about looking for life on Mars, so the science, and also how it is kind of to work on a NASA mission on Mars. And as Karin mentioned, I work at the RISE Research Institute of Sweden, and I'm based in Stockholm. So who am I? In addition to being a research scientist, I'm currently part of the NASA Perseverance rover science team. And my correct title is a participating scientist return sample science. So basically my task, the selection was when, so one of Perseverance main objectives is to collect samples for so-called Mars sample return, where the idea is to collect some sample and then send them back to Earth. And therefore they decided to have like a number of people who are kind of experts on the analysis of these type of samples on Earth. And this is what we do as a return sample scientists. Basically, we help select samples to be collected, and another important part is to document also all the information we have about these samples. My additional background in space is I participated in several space missions as a scientist. I was a co-I or co-investigator on the COSIMA instrument on the ESA Rosetta mission to the Comet 67P. I'm also currently a co-I or co-investigator on the MoMA instrument on the ESA ExoMars rover to be launched in 2028. So what's my background? How did I get here? Well, I started by doing a Master of Science in Engineering Biology. The Swedish title was Teknisk biologi in Linköping University. So it was kind of far away from space, but I was actually already interested in astrobiology at that point. So I kind of wanted a broad, and astrobiology is a very broad subject because it involves biology, geology, and chemistry. And what I haven't studied at all actually was during my master's was geology, but I did get like the chemistry and the physics and the biology. So actually when I applied for a master's thesis, I actually just saw a person, Thomas Huda, who was saying, he was presenting himself as an astrobiologist in a Swedish scientific program on TV. And I actually just sent him an email asking if he had a project, and he did have a project. So that actually led to a master's project with him, and then also a PhD with him. So I did a PhD in geochemistry, so I had to learn all my geology through my PhD. I was also at that point, they also had an astrobiology research school, so I got to interact with students in other departments at Stockholm University. So I was at the geology department, but there was also people from the biology, astronomy, and physics department. After doing a PhD, I did a postdoc for a year at the Carnegie Institution of Washington in DC and the Smithsonian National Museum History. Both of them are in Washington, DC in the US, where I kind of worked on specifically looking at Martian meteorites and looking at organics. So my main subject in Mars research is trying to understand if there's ever been life on Mars, and also trying to, and especially in terms of trying to find organics associated with this life material. And currently I'm a research scientist at RISE, so I kind of do basic research. So RISE is more towards the applied sciences, and most of the projects we do are actually commercial projects with industry. But I do but we can also apply for grants from, say, different research councils like VR or the Swedish National Space Agency. And so that's kind of how I get funding for my research, basically. So if we go back and how do we look for, so I just wanted to give a slight background of how do we actually look for, life on Mars. I mean, Mars today is a dry and dead planet. I mean, it's basically a cold desert. But as we look back, but if you study Mars more closely, you kind of see all these traces of past water activity. And typically when you go looking for life elsewhere than Earth, you go first looking for water, because water is kind of one of the requirements for life. And Mars do show a lot of evidence in their ancient terrains of water activity, and especially, and when we're talking 4 billion years ago. And so there's this kind of speculation that maybe 3.6 million years ago, the planet looked like that picture on the very right here. I don't know if you see my cursor. But what happened to this? Why don't we have that water? So it's still kind of up in the air what actually happened. But one suggestion is that Mars actually lost most of its atmosphere. So currently the pressure on the Mars surface is less than 1% compared to Earth. It's mostly consisting of CO2 and small amounts of methane. So it's basically the pressure is too low for liquid water to be stable, except for maybe at certain points of the day. And why was that? And this is also kind of not sure, but one speculation is that there was a magnetosphere, and that protected against the solar wind. And when that disappeared, the solar wind can remove most of the atmosphere. And there's also the size of Mars is less, which decreases the number of heat that's conserved from the accretion of the planet. And also there's less gravity to hold the atmosphere. I mean, there is water still on Mars, but it exists mostly as ice, or mostly on the poles. There's also a lot of minerals on Mars indicating that there was water. We have like phyllosilicates or clays and all kinds of hydrated minerals. And also there's also these possible detections of water in the subsurface. And if there was ever life, it probably retreated into caves. However, what's interesting with Mars, and this also applies to Earth, is that actually a very large part of the surface is very old. It's more than 50% of the surface is more than 3.6 billion years old. And if you compare to Earth, there's only small pockets of this very old rocks left on Earth, because so everything has basically been wiped out by plate tectonics, and any signs of early life on Earth has also been wiped out, or it has been very altered, because you have a lot of heat altering the rocks. So actually, by studying Mars, we're also studying the possible early origin and evolution of life on Earth. And if we look at Mars climate change in relation to the evolution of life, you can see that life on Earth actually appeared before Mars climate change, which is around 3.5 billion years ago, and life was already established at that point on Earth. So how do we actually look for life? So this is kind of an important point. Sometimes I put on that we're obviously not looking for these kind of nice classical fossils that we see here, this kind of fish or these macrofossils, because those are on Earth usually less than 650 million years old, because we didn't have much complex life earlier than 600 million years ago. So actually we're looking for this kind of not so so easy signs of life. We are looking for microbial life, and these tend to leave much less clear signs of that this is life. And as we say on Earth, as I mentioned, most of the rocks on Earth has been kind of cooked. So usually the samples are also very altered. But if we would find something like this, so this is an old fossil of a stromatolite, a likely stromatolite, which is kind of this bacterial, large bacterial colony. And if we find something like that on Mars, we would be actually jumping with joy. Actually, we kind of joke sometimes that it's always on the sample. We have this kind of potential sample list we want to find, and we're always like stromatolite. So if we're looking for life on Mars, we're actually looking for, typically we talk about biosignature, so you could be looking for those structures and texture that we saw in the previous slide, but it's also looking for organic molecules, so the main constituents of life, or different minerals that's only made by life. You could also potentially look for biochemical activity. This is not something we could do and stabilize. So the problem if you have a rover is that you won't be able to see this with the rover instrument, most of these things. The organics you might detect, but most of these structure and texture are too small for the resolution of our cameras. And we have no way to, for example, do the stable isotopes. So how do we look for life? Well, we look for Mars. There are 2 different ways. We have, of course, the landers and the rovers, and also the orbiters on Mars. So we have here Perseverance, but this is of course just one of the rovers on Mars that they're currently working. The other one is Curiosity, and there's a number of landers also. And also we look at Martian meteorites. So this is kind of what I started with when I started in this field, is looking at, actually trying to look at the only samples that we actually have from Mars. So currently we do have some samples from Mars, and these are Martian meteorites, and they were kind of hit, basically something hit there was an impact on Mars, and that threw out some rocks, and some of those rocks happens to land on Earth. And I use this kind of advanced instrument to try and understand what organic molecules there are in these Martian meteorites, and if there's any connection to certain minerals, so we can understand the source, because organics is not just associated with life, but also with you can abiotically, so involving no biological process, you can produce organics. So by trying to understand the problem with Martian meteorites in terms of looking for, is that we don't know where they're coming on Mars. They're probably coming from just a few select impact craters, so we only sampled a very small part. They're also igneous rocks, so meaning they're volcanic rocks basically. So there's no sedimentary rocks, which is kind of formed in these kind of lakes, and they are not part of the Martian meteorites, possibly because they wouldn't survive the impact. So it's very biased. So that's why we want to collect our samples with Perseverance and Ingenuity. And I had a sound from Mars, but we tested it and it was too low to actually be heard. So I guess I will post a link about that. So this is Perseverance. So Perseverance landed in Jezero crater in February 18, 2021. And it has been working since then. I think we're on salt 1,000, what was it, 12? I think we're at 1,000, 1,100 roughly at the moment. And here is why did we land in Jezero? Well, it kind of contains that things we're looking for. It's a crater, and it was based on that there's this presence of in and outlet channels. It was a lake, and in association with this lake, you have that looks like something like a delta. And both lakes and deltas are good places for life. And also an additional good thing is that a delta will accumulate material, including organic material, biosignatures, both from that lake and also from whatever's brought into the lake. And another good thing is that there's also abundance of minerals that are known to preserve organic material. So this is the Perseverance scientific goal. So in addition to collecting samples, we're also studying the geology and the astrobiology. And my role as a return sample scientist is to help choose the sample to collect, and also make sure the right information is collected about them. Because one of the problems with the Martian meteorite is we don't have any information about, where they're coming from. So here we have a chance to get all the information, not all them, but most we get like exactly where we're. So with all these samples, there's attached a whole report about all the instrumental data that was collected associated with the samples. And this is the number of samples. Actually, we are up at 20. Actually, we collected more samples than I think we're up at 27. So we sealed 27 tubes. So that include around, let's see, 21 rock cores, 1 atmospheric samples, and 2 regolith samples, and then also 3 witnesses. So this is kind of controls. So the idea is to send this home, and this is very complicated. So we are just here in the first stage, we're collecting the samples, then there's an idea of having a rocket to send those samples to space, and then that rocket will release this kind of like a small orbiting canister here that will be put up by another spacecraft, and that would actually return the samples to Mars. And the samples are earliest by 2023. Now there was a whole report, so this is all up in the air. So we actually don't know much at all how this is going to happen, but hopefully we'll. So that's kind of a reality of working on this mission, that we don't actually know. We're kind of also controlled by another mission, the Mars sample return. So we cannot just do exactly what we want, because we're also, as we will probably be part of delivering the samples to the rocket that launches into space. It will be, we have to also, we're also controlled by the Mars sample return. So this is kind of one of the things of working on this mission, because it's kind of, there's new things happening every day. So this is kind of a rough description of how it's working. So normally I work kind of until, I don't know, 5 o'clock. I work on other things or related to this, and then I have a lot of meetings in the evening, because this is run from JPL, so it's American West Coast. So when it's 9 o'clock there, it's actually 6 o'clock already here. So I think yesterday I had a meeting ending at 12 o'clock in the evening. So this is one of the disadvantages, but it's also fun. And so I also do operations. So you have defined roles where you, because we need to collect the data, right? So there's a number of science rules every day to collect this data. And the team, it's a huge team. It's a team made out of 400 scientists. Not all of them are that active, but they're all from all over the world, though. To be fair, it's most of them are from the US, and then there's a lot of people from Europe and a couple of people from Australia. So not much outside of that. And let's see. And if we look at planning on Mars or operations on Mars, is we plan typically 1 sol a day, except for Fridays and holidays, when we've planned 3 sols a day. So if you don't know, a sol is 1 day on Mars. And however, the planning is, of course, done in several stages. We have a strategic planning where we plan an entire campaign. So at the moment, we're actually planning a new campaign, because we're about to leave the crater and actually go outside and explore outside, because there's a lot of ancient rock outside Jezero, which is older. So we're very interested in going there. And then, so we're actually planning this, and then we'll decide kind of where we want to go. And then we have the campaign planning, which is made for maybe a couple of 1 or 2 weeks to decide kind of exactly, we kind of want to go there, where we want to drive exactly on the route, and then also kind of which measurements we want to do. And then we have tactical, where we actually decide, okay, we want to shoot at that rock. And for example, in tactical, I would serve as a targeting scientist, and this is a person who suggest, oh, we want to look at that rock versus that rock, because we are looking at the diversity of this particular unit. We're in the margin unit, and I get to name the target based on it's a list. There's a list of names, and these names are from national parks in the US, or from the world, actually. So this is kind of just how a day, and that's actually my last slide, and I might have gone a little bit over time, but so that's all for me. So